13.4 deals with arithmetic series and sequences. A sequence is arithmetic if there's a common difference that remains the same throughout the sequence. So for example, 3 to 5 is an increase of 2, 5 to 7 is an increase of 2, 7 to 9 is an increase of 2, and 9 to 11 is an increase of 2. So we say that this series is arithmetic. It has a first term of 3 and a common difference of 2. Example 2, the first difference is 3, but the second difference is 6, and so we immediately know that this is not an arithmetic sequence. Once you know that a sequence is arithmetic, you might need to find a certain term. The way that you find that is you look for patterns. If A1 is 3, using this arithmetic sequence, A2 takes that first term and adds one of the common differences. A3 takes the first term and adds 2 of the common differences. A4 takes the first term and adds 3 of the common differences. These numbers are all working out to the numbers that we see in the sequence. And so to extend this further, for a general formula, the nth term is the first term, or a sub 1, plus 1 minus the number of the term that you're looking for. So for example, since I want the fourth term, I use the common difference 3 times. When I needed the third term, I used the common difference twice. So I'm going to use the common difference n minus 1 times. And this is the formula that's used to predict terms in an arithmetic sequence. So to look at an example, if I know that the first term is 3, and if I know the common difference is 2, and if I'm asked to find the 75th term, I start with my formula and say that the 75th term is the first term plus 75 minus 1 times the common difference of 2. 3 plus 74 times 2 gives me a total of 151. So I know that the 75th term is 151. Second example, first thing I'd see is that the first term is 2/5. I'd notice that each term is increased by 2/5, so the common difference is also 2/5, and I'm asked to find the 30th term. So using the formula, a sub 30 is going to equal the first term plus 30 minus 1 times the common difference of 2/5. Well, the first term was 2/5, and when I take 29 times 2/5, I get 58/5 for a total of 60/5, which winds up equaling simplifying to 12. So the 30th term is 12. So two examples of how to find the nth term of an arithmetic sequence. This third example is a little bit trickier. They don't give us the first term or the common difference. They just tell us the difference between the 10th term and the 20th term. And while I don't have much to work with, I do know that there's a formula for the 10th term that says the 10th term is the first term plus 9 times the common difference. And again, this 9 comes from the fact that inside the parentheses is n minus 1. I know that the 20th term is going to be the first term plus 19 common differences. I'm also told that if I subtract the 10th term from the 20th term, or actually subtract the 20th term from the 10th term, I wind up with a difference of 70. So I'm going to take and do that to my two equations here. A10 minus A20, I was told, is 70. A1 minus A1 cancels out, and 9D minus 19D gives me a negative 10D. If I divide both sides by negative 10, I wind up with the common difference of negative 7. That means that your sequence is going to decrease by 7 units for every term. This is Carl Friedrich Gauss. The story says that when he was 10 years old, sitting in his math class, he was such a pain in the butt that the teacher told him to go in the corner and find the sum of the first 100 numbers. The teacher figured that would keep him busy for a while and he wouldn't cause any more problems in class. Unfortunately, Carl Friedrich came back in just a few seconds and had the answer, and when the teacher sat down and figured out the sum of the first 100 numbers, turns out that Carl Friedrich did it correctly. His shortcut goes like this. Most of us read from left to right, so to find the sum of the first 100 terms, you would do 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, etc., etc., etc. Carl Friedrich matched up the largest and the smallest and got 101. And then he matched up the second and the second biggest and got 101. And then he did the same, and notice that there's a pattern. Every pair of numbers, if you go from beginning to end, equals 101. And if there's 100 numbers in the list, there are 100 paired numbers, which is 50 pairs. 50 times 101 winds up equaling 50/50. So the reason why this story is famous, even if it's not true, is that this is a shortcut way of remembering how to find the sum of the first n terms in an arithmetic sequence. Adding the sum of the first 100 numbers is an arithmetic sequence because you're starting with 1 and you're going up by 1 each time. We're having a common difference of 1. The shortcut, or the way to remember, is take the first term, add on the last term, and realize that however many terms you have are going to be paired up n over 2. So this is the formula that we use for the sum of the first n terms of an arithmetic sequence, or in other words, how to find an arithmetic series. Now your book is going to rearrange these terms a little bit. The way the book writes it is they put the n on the outside and they move the 1/2 inside, so they'll write a1 plus an over 2. The goal is that you understand where this formula comes from, and that way you won't have to memorize another silly formula. You'll just naturally know that the first and the last get added together, and then n minus 2 represents how many pairs there are. So while the story about Carl Friedrich Gauss inventing this formula is not true, most people believe that an Indian man named Aryabhata invented it many, many, many years before Carl Friedrich Gauss. And nobody knows what Aryabhata looks like, but this is a statue that was created by an artist who made his own picture of what that man looks like. So to use these formulas, two examples: find the sum of the first 50 terms with first -8, so a1 is -8, and 50th term 139, so a50 equals 139. The way we do this is we say, well, the sum of the first 50 terms is, using my formula, a1 plus a50 times, since I'm looking for 50 terms, n is 50, cut in half. -8 plus 139, 50 cut in half is 25. 25 times 131 winds up equaling 3,275. So the sum of the first 50 terms is 3,275 for this sequence. So the next example gives us information about the 5th and 50th terms. It says the 5th term is 3 and the 50th term is 30, and we're asked to find the sum of the first 10 terms. While I don't know what the first term is and I don't know what the common difference is, I do have formulas for finding the 5th and 50th term. So if I use those, the 5th term is equal to the first term plus 4 common differences. The 50th term is equal to the first term plus 49 common differences. And when I substitute in for a5 and a50, cross this out, use 3, cross this out, and use 30, I have two equations and two unknowns, so I can solve the system by using the subtraction method. 3 minus 30 is -27. a1 minus a1 cancels, and 4 minus 49 is a -45d. So by having the a1's cancel out, I can solve for d. d equals a -27 over a -45, and that reduces down to 3/5. I can take that, plug it into the first equation, the easier one. I know that 3 equals a1 plus 4 times, and I just found d, which was 3/5. So I have 3 equals a1 plus 12/5. Bring the 12/5 to the other side. 3 minus 12/5 is 15/5 minus 12/5 equals a1. So a1 equals 3/5. Find the sum of the first 10. Now I can use my formula. The sum of the first 10 is the first term plus the 10th term times n over 2. So I'm looking for the 10th term. I know that it's equal to the first plus the 10th times 5. Well, we know that the first term is 3/5, and we know the common difference is 3/5. And I know I'm looking for the 10th term, but how do I find the 10th term? Well, I need to use my a1 plus n minus 1d formula. So the 10th term is going to be 3/5 plus 9 times the common difference of 3/5. 3/5 plus 27/5 is 30/5, which is 6. Substituting that in back here, plus 6, I'm finally ready to finish the sum of the first n terms. 3/5 plus, I'm going to get a common denominator and say that this is 30/5 times 5. Well, the 5 is going to cancel out with both of those, so I wind up with the sum of the first 10 terms is 33. The important part about this problem is that if you don't know this part for your sum formula, you would just substitute in the term equation that we used earlier. So an alternate version of the sum of the first n terms is a1 plus, and if I need an, we know that the an formula is the first plus n minus 1d, a1 plus n minus 1d, and simplifying that, we get 2 a1s plus n minus 1d times n over 2. So if you need the sum of the first n terms and you don't know the nth term, but you know the first term and the common difference, this is an alternate version for the sum of the first n terms formula. So we finished the examples on this page, and the final example involves more summing. I have a first term of a1 equal 1 over e. I have a common difference of 2 over e, because it looks like 3 over e minus 1 over e is 2 over e, and I'm asked to sum until I hit 21 over e. Well, I don't know which term this is, but there is a formula that says if you want the numbers to alternate over the evens, or if you want every odd term, this formula for the numerator is 2n minus 1. If you plug in numbers for n, you will get results that are only odd numbers. Well, which term, which n value produces 21 in the end? 2n is 22, n equals 11. So if you count it up, this would be the 11th term. So if I want to find the sum of the first 11 terms, I'm going to have a1 plus a11 times n over 2. And I get 1 over e plus 21 over e times 11 over 2. And this summation formula works even if you have an odd number of terms. 22 over e times 11 over 2 produces 121 over e. Sum of the first 11 terms for that sequence is 121 over e. The final example combines sigma notation with arithmetic series. This time I'm starting at 5. So when I plug 5 into my formula, I have 2 times 5 is 10 minus 1, which is 9, plus plug in 6, I'm going to get 12 minus 1 is 11, plus plug in one more, 7. 7 times 2 is 14 minus 1 is 13, plus dot dot dot. And when I plug in 100, I get 200 minus 1, which is 199. I need to find the sum of these numbers. I know that the first term is 9. I know the common difference is 2. I don't know which term this is. So when I plugged in 5, 6, 7, and 100, the n that I'm using is an index for this sigma notation, but what I really need to know is what term this is. This is the first term in our arithmetic sequence. This is the second term. This is the third term. And if I compare the term number to the n that I used to plug in, it looks like the difference is always 4. So this number is 96. 5 minus 1 is 4, 6 minus 2 is 4, 7 minus 3 is 4. So when I plugged in 100, I'm really finding the 96th term. So to find the sum of the first 96 terms, I'm going to take the first, the 96th, and multiply it by n over 2. The first term is 9. The last term is 199. There are 96 terms cut in half. 9 plus 99 is 208. 96 divided by 2 is 48. And 48 times 208, 9,984. So the sum of the first 96 terms, 9,984. So that's it. Mostly just 3 formulas, one for finding an individual term, one for finding the sum of the first 10 terms, written 2 different ways. The Gauss method, where you add the first and the last, or the way that we saw on this screen, where you knew the first and the common difference. You'll get used to using those formulas, and you'll use them so much that you'll eventually get them memorized. That's it.